Hi everybody, welcome back to Happy Little Diodes. We are continuing our journey into reverse engineering ZX Spectrum mods today with this thing. Now this is one that doesn't seem to have cropped up before on the online forums that we use at least, and it's taken me a while, but I've got to the bottom of it I think, although I do have a couple of questions which I haven't been able to fully resolve, so I'm going to hand that over to you. If you make it to the end, let me know what you think. If you haven't watched the previous video on the ATK mod, I recommend you check it out because this is going to build on what we learned in that video. Before we get into it, let me just say thank you to everyone who's joined me so far on Patreon. The support really does encourage me to continue making content, so thank you very much. Right, let's get into it. So here it is. This is the machine that we're going to take to pieces. It's been sent to me very kindly by Colin. Thanks, Colin, for sending me this. It has driven me mad, but that's a good thing because I've learned a lot along the way. Having a look in the back, you might think, hey, there's something funny going on with this machine, and you'd be right. There's definitely a PCB in there, upside down on top of the main board, and if you're thinking, hey, that's an issue 1, I'm going to buy that really quickly, well, it's not. An issue 1 looks like this. You're looking for these ceramic capacitors. That being said, this is definitely an interesting machine, and we're going to have some fun picking it apart. The serial is low. It's not issue 1 low, it's about issue 2 low, and the 48K sticker on there tells us that it is at least an issue 2, which has had an upgrade. Now, if you haven't seen the previous video in which we picked apart an 80K upgrade for 48K Spectrums, I recommend you go and check that out now. It's going to help with following along with this one, because this is kind of going to pick up where that one left off. That being said, I'll give you a very brief summary. There's a link here on the board which forces 5 volts or 0 volts into one of the address lines, which is fed to the upper memory when we're reading from or writing to it. The effect of this is to close off one half of the upper memory, so we only use what's known as a good half of that memory. If we can remove that link and manipulate the voltage going into that middle joint, we can effectively select a bank of memory. We can split the upper RAM in half and get access to another 32 kilobytes. Mods such as the one described in the last video, and spoiler alert, this one, enable us to do just that using software commands. So this is the mod we're looking at today. It's a lot more complicated than the previous one, although thankfully I've got this one on the desk in front of me. It should be a bit easier to pick apart. The underside of the board doesn't seem to have any modifications as I can see, only a lower RAM repair, which I'm not going to bother myself with because it seems to be working, even if it is a little bit fluxy. It looks like we've got 5 logic chips involved with this mod, and a capacitor and a couple of resistors. I think it's safe to assume that this is trying to do a little bit more than the simple 80K mod was doing in the previous video. There's a lot of signals being picked off the board here, all these different coloured wires. We'll figure out what they all are, and turning it over, taking off the sticky tape, we can have a look at what chips we have, and we can see it's a one-sided PCB, which is going to make life a little bit easier for us. Before we open MS Paint, let's have a closer look. It says copyright SCD. There is a theory that this mod could be something from Television Services of Cambridge, just because there was an advert in a Sinclair user magazine which seemed to match it, but that advert talked about cutting traces, and I can't see any cut traces on this mod or on this board, which means it's not that particular mod, or maybe it hasn't been fitted correctly. Another interesting thing is the ULA is a misprint. It says -S at the end instead of -5, which is an interesting little quirk. Okay, have you got a cup of tea? Because we're about to get into it. We're going to be using this picture of the bottom of the board and this picture of the top of the board to trace where everything's coming and going, and hopefully represent all the information we need to know to understand what's happening with this mod. This is all open to interpretation. I do still have questions about this, so get involved in the comments and let me know what you think's going on. So first up is this blue wire, which is connected directly to the middle joint on the link here. The link has been removed, so I'm going to call that bank select. That's an output of the mod, I assume. There is an unpopulated joint here, which connects to 3 of the pins of the chip on the left hand side. We'll look at that later. We have refresh coming in here on the green wire, which connects to 2 pins on the leftmost chip. A white wire here, which is carrying A15, which is connected to 1 pin on the chip in the middle there. The brown wire is carrying int, our interrupt signal, which is an active low input to the Z80. By the way, refresh is an active low output of the Z80. The red wire is sensibly the plus 5V supply, which thankfully goes to all 5 chips, so that makes sense. A15 is also here on the yellow wire. So what's going on here? It must have been kind of intercepted from the board, and we'll have a look more closely at that, but let's just assume that the white A15 is the output and the A15, which is yellow, is our input. The 8th bit of the data bus, D7, is here coming in next to the letter C. It connects to 2 pins on the chip in the middle there. We also have reset, which is an active low input to the Z80, and I'm assuming that's got something to do with initialization, as opposed to the mod having some mechanism to reset the machine. We have another bit from the data bus D0, which is the first bit. There it is, it's connected to 2 of the chips, one on the middle and the one to the right of it. Continuing moving left to right, we have an active low right signal, which is here on the upper right of the board, going down to one of the inputs of the rightmost chip. Nearly there now. Moving on, we have ground connected to all 5 chips, thankfully, and another bit from the address bus, which is A1 connected to 2 of the pins on the rightmost chip. We've got active low read here in blue, which is just going to 1 input on the rightmost chip, and finally in red we have IORQ, or I've drawn an IO rec here. It's an input-output request, and that is a signal which is active low and sent from the Z80. Okay, good, that's all our inputs and outputs. Don't worry, we don't need to memorize them, we're going to keep building up one step at a time. So let's flip it over and look at what chips we have. This is the top side of the board, it's just a still from the video earlier. So let's start identifying the chips from left to right. This is going to be very useful. This is a truth table for a NAND gate, and here's why. The chip on the left hand side is a quad NAND gate chip. Lovely. And the next chip across is identical. So we have 8 NAND gates to play with. Actually, that's not completely true. We have 12 NAND gates to play with, but the 4 on the right here from a different chip, this is a 74LS03 chip. And the difference here, which I've marked with a little squiggle, is that these are open collector outputs. Now what does that mean? Well, let's take a transistor. Here we are, collector on the top, base on the left, emitter on the bottom. And let's also not forget that these are TTL chips, transistor logic. They achieve their function using transistors, and the transistors inside this particular chip are arranged with an open collector on the output pin. Now what does that mean? Let's simplify it. We have a NAND gate here, but we can draw it like an AND gate leading into a transistor. And you'll notice that I've replaced the collector text with the word output, because that is one of our 4 output pins on the chip. And ground obviously also all links up to the ground pin on the chip. Let's look at our truth table. Here is a truth table for an AND gate. We can see that the output of that AND gate is either 0 or 1. So 0 volts or 5 volts, as we would normally expect. Let's say we have a 0 on the output. What does that mean? It means that the base of our transistor is kind of switched off. It means it's not going to conduct from the collector to the emitter or from the top to the bottom. So that's the difference with this chip. In this state, the collector or our output pin isn't really connected to anything. It's high impedance. Or you might say that it's floating. The alternative is when the output of the AND gate is 1, there's going to be some voltage at the base, the transistor switches on, and we can conduct from our output pin to ground, so the output is basically forced to 0. What this means for us, if you look at the truth table in the top left, wherever you see a 1 there, if you're thinking about the chip in the middle with the open collector outputs, replace the 1 with a Z to indicate high impedance. Moving on, the next chip is a T74LS4AB1, and that is a dual flip-flop. It looks something like this. There's a data input, a clock, an output, and an inverted output, and there'll be some kind of set and clear mechanism. We'll get into more detail on that soon. Our final chip, the 74LS27, is a triple 3 input NOR gate, and that's not open collector. Here's a truth table. The interesting one is the top row. When all the inputs are 0, we get a 1 on the output. So all good so far. We know our inputs and outputs, and we know what our chips are. Let's start with the triple input NOR gates. And here's the diagram from earlier which shows the signals moving around on the other side of the PCB. Straight away we can see that we have no connection on pins 1 and 2 and 12 and 13, we must only be using 2 of our gates. This is futile, but I'm going to delete that to try and keep things from getting too messy. Things are going to get messy. Let's mark our inputs to the first of our logic gates. We've got read active low, we've got IORQ also active low, and we have A1. Read will be low when we're trying to read from memory, so will IORQ, and A1 is just the second bit of the address bus. Let's remember the truth table for a triple input NOR gate. The interesting row is the top row. When all of these are 0, we'll get a 1 on the output. So to me that means the output of this logic gate goes to 1 when we have an input-output request to read an address with A1 low, so bit 2 of the address bus is a 0. The gate on the right hand side is almost identical. It has A1 and IORQ, but in this case it has write, which is active low, instead of read. So the output of this gate goes high if we have an input-output request to write to an address with A1 low. Okay, so the purpose of this chip is to generate two signals. One tells us that we're trying to do a read associated with the mod, and one that we're doing a write associated with the mod. So that seems pretty simple. Let's move on and see where these signals go. Returning briefly to the bottom side of the board and our markup that we did earlier, we're going to see where these two signals go. Let's also start building up our schematic. I think it'll be helpful to do this as we go along, because in the end it's going to be quite a complicated schematic. So here's our two NOR gates which are in use. Let's put our inputs in. The top NOR gate here is receiving read and IORQ and A1. The bottom NOR gate also receives IORQ and A1, but it receives write instead of read. Easy so far. Let's trace where the read signal goes from the output of the top NOR gate here in blue. Goes all the way over there to two inputs of the chip on the middle. Going to highlight it blue on the schematic and call it the read command, and we can see that it goes into an input of an open collector NAND gate. Before we trace that any further, let's look at the write command. I'm going to colour that in green, there it goes, and it goes to two inputs of the second chip from the right. I'm going to draw it green on the schematic and call it the write command, and we can see that it goes into the clock input pin of a flip-flop. Tracing this a little bit further, it also goes to the clock of the other flip-flop on that chip. So our write command is clocking both of our flip-flops. We'll go into the flip-flops in more detail later, but basically when the write command clocks the flip-flop, whatever's going in on pin D, our data input, will come out on Q, our output, and we also get an inverted output on the pin /Q. Now I did say that read connects to two inputs on the OpenGate NAND collector chip, and we'll go into that in a bit, but for now let's go over to that chip and have a look what's going on there. So 74LS03 is our chip in the middle, with the darker coloured chip there. Let's draw on top of it our gates, there they are. Those are our four 2-input open collector NAND gates. For reference on the top left, here's a diagram that we scribbled on to show where all the signals are going. So let's start marking it up. We first of all have our read command, which we just deciphered, going in on pin 1. That's this one, the output of the NOR gate. Don't get it confused with read from the Z80. The second pin, the second input to this NAND gate, is one of the outputs of one of our flip-flops. So this is a state 1 or 0 which we are able to control within this mod. The output of the NAND gate goes into the input of that flip-flop and is also connected to D7 bit 8 of the Spectrum's data bus. We'll figure out what's going on here once we've identified the rest of the inputs and outputs and drawn it on a schematic. So pin 4 is the same flip-flop output as in pin 2. That's going into the second NAND gate along with A15. And where does the output go? That's pin 6. Well, it's connected directly to both inputs of the NAND gate in the bottom right. That's pins 9 and 10. The output of which is A15 getting put back into the ZX Spectrum. So it must be borrowed at some point within the Spectrum schematic into pin 5 of this chip, and the output is spat out on pin 8 back into the Spectrum somewhere. We'll have a look in a bit more detail shortly. Now remember that I said the output of these NAND gates, which are open collector, will be high impedance or floating in some conditions. That is a characteristic we can take advantage of, but the designers have decided they don't want to take advantage of that for this particular output on A15, so they fitted a pull-up resistor. And this means whenever the output of this gate is high impedance, it will be effectively 5 volts or 1 shown on A15. If you like, it turns it into a normal NAND gate with a truth table like this one. Okay, good so far. As I mentioned, don't worry, we're going to figure out the function of this in a minute. Let's just finish off these pins. We have the read command is also going in on pin 13. It's an input to the top right NAND gate. The other input to this NAND gate is the flip-flop output from the second flip-flop of our dual flip-flop chip. And much like the output on pin 3, the output on pin 11 connects to D0, the first bit of our data bus, and the flip-flop input, the data input of that flip-flop. So we kind of have three functions coming from this chip. We have one in the top left, which is some kind of read command. The bottom two gates give us some kind of interference with A15, and the top right gate gives us another kind of read command. Okay, let's draw it. So we know the first bit. We have a read command coming here from the output of one of our triple NOR gates. We also have a write command from the other NOR gate. There we go, we'll keep highlighting them blue and green. The write command is clocking a flip-flop. Let's compress the diagram a little bit to make some room, and let's number the 4 NAND gates in our chip. So we'll start with gate 1. The inputs to gate 1 are our read command and the inverted output of the first flip-flop. I'm just going to draw the second flip-flop in actually as well, just for completion. Okay, what else is happening with gate 1? Where's the output going? It's going to the data input of the first flip-flop, and it's also connected to D7 bit 8 of the data bus. If this wasn't an open collector output, we'd have an issue here because D7 would be forced to 1 or 0 depending on what's going on with this chip, and that would interfere with the data bus and the spectrum would crash. But we're using an open collector output. So where we would normally have a 1 or 5 volts coming out of the output pin, if it was a regular NAND gate, we've got high impedance or a floating output. You'd be right in thinking that could also be bad. You don't want a floating value on the data bus, but if we consider our two cases here, we can either have 0 on the output, so the output pin is pulled to ground. Nothing wrong there as long as the data bus isn't in use by anything else on the board at that time. Or we have high impedance, and this could be bad because you don't want the floating data bit, like we said. Well, let's have a look at the schematic, and let's assume that all of the data bits are in high impedance on the Z80 and the ROM and everywhere. Well, that's not so bad because we can zoom in down here and we can see that there are pull-up resistors already there. There's 1 pull-up resistor per bit on the data bus, 8 in total. So that effectively changes our truth table to 1s on the output because we have the pull-up resistor, or when the spectrum's in normal operation, it will just be doing whatever D7 would normally be doing. Okay, so that's that cleared up. Let's move on. In fact, let's draw D7 over on the left here. I think that's going to be a bit neater when we fill up this schematic. And before we move on, let's just think about what's happening here then. We have a read command that we can trigger with some line of code, and that goes into gate 1 here, and the output is going to be either 0 or 1. So D7 in the result of the read command is going to be 0 or 1. So if you do a bit of maths, if D7 is 1, the result as a decimal integer is going to be 128 or higher. If D7 is a 0, it will be 127 or lower. So we have a mechanism here to read out the state of our first flip-flop, but what does the state of our first flip-flop mean? It either means it's our selected memory bank of upper memory, or it could mean something else, because remember we have 2 flip-flops here, so let's not jump to that conclusion, and let's have a look what else is happening here. Moving on to gate 2, let's draw it here, we can see that it is receiving both A15 and the output of the flip-flop we were just talking about. If we trace the output of gate 2, it goes into both inputs of gate 4, and the output of this goes off to A15 with a pull-up resistor. Let's draw some numbers on and figure out the function of these 2 gates. Let's say that the state of our flip-flop is giving us a 1 here on the input to gate 2. That kind of isolates us to the bottom half of the truth table here, if one of our inputs is kept at 1. And let's say A15 is 0 at a certain point in time, well, we must get a 1 on the output of gate 2, which means we have a 1 on both inputs of gate 4, and that's our interesting row. It means we get a 0 on the output going back into the board where we've intercepted A15. The other version of this state where the flip-flop is outputting 1 is when A15 is 1, then we must get a 0 on the output of gate 2, which means we get a 0 on the input of gate 4, both inputs of gate 4, meaning the output is 1. So A15 is basically being passed through. When it's a 0, we get 0 coming out, and when it's a 1, we get 1 coming out. So what about the other case? What if our flip-flop state is giving us a 0 on the input to gate 2? Well, let's try it out. We're isolated to the top half of the truth table here, which is a fairly simple case. It means whatever A15 is doing, we're going to have a 1 on the output of gate 2, which means we have a 0 on the output of gate 4. So it seems to me that we can force A15, at least on the part of the board that we're spitting it back into, to always be at 0. Now that's interesting, so we have a flip-flop state which kind of disables A15, but we need to look at the schematic now to see what's going on. So let's open up an issue 2 schematic. Here it is. I can tell you from inspecting the mod that A15 is picked up from the Z80, which is up here in the top right, and it's deposited in the bottom right down here in this cluster of logic. So let's cut out those two bits of the schematic, Z80 on top and the logic on the bottom. This logic is used in the addressing of upper memory, by the way. So let's join up A15, there it is coming out of the CPU and going into the logic in the bottom. And let's draw in our little mod which we've put in by intercepting A15. By the way, how was it intercepted? You'd think you'd have to cut a trace, but I've already told you that hasn't happened here. Well, can you see it? There it is, that's where it's being spat back into the board, and they've just bent the pin up out of the socket, which is nice, non-destructive. Anyway, going back to the schematic, we have the flip-flop state going in on the bottom here, the second input to gate 2, and we've already established that if this is a 0, we freeze A15 at value 0, and if it's a 1, we pass A15 through. And A15 goes through to pin 10 of IC24 here, and let's just draw a truth table of a NAND gate because we're going to figure out what effect this has on the addressing of the upper memory. So let's freeze A15 at 0, it isolates us to the top 3 rows of the truth table, so this gate on IC24 must have an output of 1 all the time. Now let's switch rails down here to the MREC signal which is coming in at the bottom. MREC is active low and it's active when we want to read from memory or write to memory. So it's going to be low if we have a memory operation, which is what we're interested in here. It's going into this OR gate, 2 zeros into an OR gate give us a 0, so this must be just some kind of a delay for timing purposes. And if we trace the output of the OR gate, we can see that it goes directly to the CAS input of the upper RAM chips. Oh wait, hang on, we figured this out in the last video. Those are swapped on the schematic, so it's actually going into the RAS. Yeah, we must fix that schematic. Now if you're saying what the hell does RAS and CAS mean, I encourage you to go check out the previous video on the ATK mod where I explain it in excruciating detail. So our upper RAM receives its RAS strobe during a memory request like normal. The MREC signal, the low signal, also goes into this OR gate where it's ORed with 1. Remember, we've frozen it at 1. That means the output of that OR gate is always 1. Consequently, the input to IC23 pin 5 on the left there is always 1, which means the output on pin 6 is always 1. And that means that CAS is always 1. It never goes low, it never goes active. It means the upper memory never gets its full address, and we've effectively disabled upper memory. It's going to stay in high impedance all the time. So our first flip-flop that we can manipulate disables upper memory or enables upper memory. We can switch it on and off. So if we just roll back to our flip-flop, the top left here, what this is going to allow us to do is read the state of upper memory. We can read out a value 1 or 0 on D7 and it will tell us if upper memory is switched on or off. And we also now know that using a write command we can change the output of the flip-flop in the bottom left, flip-flop 1, to switch upper memory on or off. So good, I think we're starting to get somewhere. Let's continue drawing the schematic. So here we go with gate 3. What are the inputs to gate 3? Well, we have our read command, that's the blue line there, let's plug that in. We also have a flip-flop output, and that is the flip-flop output of flip-flop 2. There it is. Tiny little nuance, it is the inverted flip-flop output, which is the same as we had on flip-flop 1. The output of gate 3, like we had with D7, is connected to D0. and again that goes into the data input of the flip-flop. So what is a function of this gate 3 in our open collector NAND gate chip? Well, it's going to read the state of flip-flop 2, and I'm going to assume that that is the signal which controls the paged in bank of the upper memory. So we can use a write command to switch upper RAM on and off, we can read the state of that flip-flop, we can use a write command to switch between banks of the upper memory, and we can use a read command to read in the state of that flip-flop. So when we do that, we'll get an integer number where D0 is either 0 or 1. If you think about it, if D0 is 0, the number will be even, and if D0 is 1, the number will be odd. So the odd or evenness of the number tells us which bank of upper memory that we're using. Okay, we haven't looked specifically at the flip-flop chip yet, so let's go there. I know we've brought them in already because we needed to explain what was going on with these NAND gates, but let's have a look so we understand everything that's happening with these flip-flops. So far I've drawn them like this, but here's our chip, it's a 74LS74AB1, and it's more accurate to use this little picture which I got from the datasheet. We have the pin designations on as well, and we have that for the second flip-flop too, so that covers the whole thing. I'm going to change all these letters to words, so pin 2 is data, that's our data input, and pin 3 is the clock input. We have set and clear on pins 4 and 1, those are active low. And then we have our data output, we'll still call that Q on pin 5, and the inverse of the output on pin 6. It's identical for the second flip-flop. Let's bring back our little traced diagram here, there it is, and we need to figure out what's going into all of these pins, make sure we haven't missed anything in our previous analysis. So that's where our chip sits. I've drawn it mirrored there because we're looking at the bottom side of the board, and let's go. The most interesting thing that we've missed so far is what's going in on the clear pin, and that is reset. I'm making it flash on the diagram, it's there in the middle. And I think we've got everything else figured out. We have the write command, which is clocking the flip-flop. We have D0 on the data input pin of the first flip-flop, and we have D7 on the data input pin of the second flip-flop. We also have no connection on set and the data output pin Q on both flip-flops, and on the output, let's start with the second flip-flop, we have our disable upper RAM, and on the first flip-flop we have our bank select. As I mentioned, I don't think it's massively important that we're using the inverted output of the flip-flops. As long as we switch between one state and the other, everything should work out fine. The interesting new thing here then is the use of reset on the clear pin, which is something to do with initialization, so let's figure it out. The reset signal when you first power on starts low and then it ramps up high. Remember, it's active low, so it climbs up to its inactive state. This is achieved by simply using a capacitor which charges up when power is applied. Let's have a look at the datasheet of these flip-flops and figure out what's happening with the clear pin. That's the reset brackets clear there on the second row. In fact, let's just delete everything we're not interested in. So, clear. When clear is low, remember it's active low, it's going to force the output Q to low and the inverted output Q bar to high. And I think the reset signal should take long enough to climb up high that these states are bedded in. If you're thinking, hey, the datasheet says that the set pin should be high for this to happen, well, I agree with you, and I think this was probably just a cost saving measure, and it seems to work anyway. So assuming it does work, let's draw the output. We see that the bank select signal goes to 1, and the disable upper RAM signal goes to 1 as well. So let's just say that we're in bank 1, we'll call it bank 1, and oh, I haven't used a very good naming convention here, let's flip that around. So we have a 1 coming out of the upper RAM disable. What that actually means is upper RAM is enabled, as we figured out earlier. So I'm going to put a bar there, so it's active low disable upper RAM. We'll fix that later. So we figured out what we can do with this mod, but how do we do that? Let's talk about the memory banks first. How do we switch banks? We'll focus on flip-flop 1 here. We'll bring in our schematic here of our read and our write command. So what we need to do is some kind of software command to write to an address where A1 is low, and that will set all of our inputs to this NOR gate to 0, which means we get a 1 on the output. And what do we write to that address? Well, we either write a number where D0 is 0, like 0, or we write a number where D0 is 1, like 1. And not forgetting that we're using the inverted output of our flip-flop, if we use the command out, which is our write command, we use out to an address with A1 low, and we write data with D0 high, then our output is going to be 0, or our selected bank will be 0, which we could refer to as bank 0. So this command would simply be out 0 1, and that would switch us to bank 0. And vice versa, if we want to switch to bank 1, well, we need to write a data value with D0 low. So this would be out 0 0, and that would switch us back to what we're calling at the moment bank 1. So that's fairly simple. I think that makes sense. How about our other flip-flop? Here it is on the right there. That's our upper RAM enable or disable, however you want to call it. In fact, let's just fix that now. The output of this enables upper RAM if it's 1. There, that's easier to understand. And let's go through how do we switch upper RAM on or off. Well, again, we're using a write command, so we're going to use the out command, and this time we need to manipulate D7 in the data that we put into our out command. So we could write something like out 0 128. That forces a high value into the data as we clock it with the write command, and the output switches to 0. That disables upper RAM. And on the flip side, we might write something like out 0 127. That D7 is low, and that would force the output to high, and that switches upper RAM back on. So hopefully you're all screaming at me, why the hell do we want to disable upper RAM? Well, the reason is the stack. The stack is a location in memory which contains important stuff for the execution of code. I don't need to go into it more than that, just know it's important and it's generally put into upper memory. So let's take a look. Here's our memory map. We've got the ROM in 0 to 16K, lower RAM in 16 to 32K, and our upper RAM is 32 to 64K, although in this case with this mod attached, we have 2 banks of upper RAM. Let's call them 0 and 1. And we initialize into bank 1, and that's where the stack goes. So we're happily working away in bank 1, and let's say we want to switch to bank 0. Here we go, let's color it in blue. What happens now? The Z80 is being happily processing away, executing its code, and within the Z80 there's a register called a stack pointer. This is an address in memory where it's remembering where the stack is. It goes looking for the stack, but because we've switched banks, it's looking in bank 0, and the machine crashes, and the machine resets. After the reset, while we're in bank 0, it creates a stack in bank 0. Now we're working with 2 stacks, which is bad, although it won't reset when we switch banks from now on, and this is the case that we had with the previous 80K mod, which we described in the last video. This isn't very good really, and the designers of this mod thought they can do better. So let's reset our little example. We've booted up this machine and our stack is in bank 1 of the upper RAM, and we do our little command to disable upper memory. What happens now? The Z80, like we mentioned before, is happily processing away. It's got its stack pointer and it goes looking, and it's not there. It can't read any information out. The machine crashes and the machine resets, and this is expected, by the way. But what happens now? Upper memory is disabled. The speccy determines that it's got 16 kilobytes of memory and places the stack in the lower memory, as if you had a 16K speccy without any of this gubbins in. Okay, then we re-enable the upper memory and we have our working stack in lower RAM. Yeah, there'll be a stack left in the upper RAM, but it's kind of obsolete now, and we can happily program away writing BASIC into our lower memory. The stack is working away in the lower memory, and we can switch between banks without affecting it, and it's pretty much a more reliable solution. But here lies one of the questions I still have about this. So the speccy thinks that it's got 16K of memory, so your code would have to be limited to the first 16K of memory, at least if you were programming with BASIC. Maybe if you were using machine language you might be able to make use of the upper memory to store your code, otherwise you've just got 64 kilobytes of handy storage in upper memory. What do you think? Comment below, I'm sure a lot of you are better software people than I. Anyway, I think we've pretty much wrapped up what we can do with this mod. We can switch upper memory on and off, and we can switch between banks, and we can read back the state of those 2 flip-flops. That's all well and good, but we still have 2 more chips on the board on the left there, and this is 8 NAND gates which are all in use, so there's something else going on with this board that we're gonna have to decipher. So let's move over to that side now. So there they are on the left there. This is 2 74LS00 chips. They're quad 2 input NAND gates. Let's start by figuring out what's connected to each of the pins. Here's our diagram from earlier, we'll start from here. So as expected, we have 5 volts going in, as well as ground. That's good. We've already identified that int is going in, that's our interrupt signal, which is active low. That's the brown one there. What about the other input to this NAND gate? Well, it's a little bit more complicated. If we start tracing around, we can see that there's a resistor involved. You can't see that, it's on the top of the board. There's a 10 microfarad capacitor involved as well. And we can trace what happens after that. We've got the other leg of the capacitor attached here, and the other end of the resistor attached to these 3 pins. Let's start here, and we can draw it on as being connected from 2 to 3, and then also from 3 to 4 and 5. Interesting. What about the capacitor then? The capacitor is connected to pins 2 and pin 6, and then from pin 6 we can see that it directly connects around to pin 9. Looking at the bottom diagram, I'm going to start tracing our bank select signal, which comes out of one of our flip-flops, doing that in yellow, and we can see that it makes it all the way over to 3 different pins on our chips here. So where does it go? Well, it goes in on pins 12 and 13, into the same NAND gate on the chip on the right, and it also goes into pin 13 on the chip on the left. So let's trace the output of the NAND gate there on the right, that's pin 11. Let's draw it in green, and we can see that it goes to pin 2 of the chip on the left, so let's draw that on there. Now let's remember the truth table for a NAND gate. If the same input's going into both inputs, we're basically going to invert it, so we can call the output on pin 11 the inverse of our bank select signal. Okay, moving on, we have refresh coming in on the left there in green. Let's draw it on, going into pin 12 of the chip on the left, and also pin 1 of the same chip. I can see that 2 of the pins are tied directly together, let's colour that in purple. And we can draw it on our chip there, that's the output from pin 11, the output of the NAND gate, into pin 4, which is the input of another gate. Can also see that pins 9 and 10 are connected to pin 6, that's highlighted white at the minute on the diagram at the bottom. And that's where that unpopulated joint was, which is marked H. We don't know what that does, but let's draw it on for completion. And then pin 8 spits out our modified bank select. Let's call it final bank select. Let's fill in the remaining gaps. There's a link here I've just drawn in a sort of beige colour. That links the 2 pins here. That's an output from a NAND gate into the input of another NAND gate. And I can also see a link here I'm going to colour in orange, and that's connecting an output from the chip on the right to an input on the chip on the left. Is that it? Yeah, that's about it. So now we can start drawing our schematic of this part of the circuit. We'll start by drawing our bank select coming in on yellow there as 2 inputs to the same NAND gate. Actually, let's number the gates. So I'm going to do 1 to 4 in red and 1 to 4 in purple. So that is red gate 3. And the output of that goes into purple gate 1. This is shared with refresh, which goes into the other input. Bank select also goes into purple 3, so let's draw that in there. And again, this is shared with refresh, that goes into the other input. I think we can simplify this a little bit. I'm going to get rid of gate 3 and just call it inverse of bank select, just for readability while we're sussing it out. Let's also flip this gate upside down so we have less wires crossing over each other. Okay, moving on. Let's see where the outputs go. The output of purple 1 goes into red 4, and the output of purple 3 goes into purple 2. We also have the output of red 4 going into purple 2, and the output of purple 2 gets split up and goes into both inputs of purple 4. And this is a signal that we're calling final bank select. So what about this complicated bit over on the right? Well, we have red 1 with int going into one of the inputs, and the other input is connected to this resistor, and the other side of the resistor is actually the output of gate 1. The output of gate 1 also gets split and goes into both inputs of gate 2, the output of which goes into gate 4, so gate 4 is now fully populated. Finally, we just have to draw in our capacitor, and we've completed this part of the circuit. But what does it do? Well, whatever the output of gate 1 is, it's going to be inverted on the output of gate 2, so there's going to be voltage across the capacitor. The capacitor discharges or charges and it will flip, so we have an oscillator. I've measured it, and the rate of the oscillator is about 50 Hz. Well, I've measured 50 Hz. It's actually not quite that if you just have a constant input, where we have the int signal. As you can see here in the simulation, I've just tied it to 5 volts. In reality, int is pulsing low at a rate of 50 Hz as the spec-e scans the keyboard, and this interrupt signal is actually synchronized with the vertical scan line retrace Interestingly, I'd recommend reading a bit more on the ULA. Check out Chris Smith's book if you want to get into real detail on that. But anyway, int is pulsing at 50 Hz, and that has the effect of making our oscillator synchronize to 50 Hz as well. So I've set up a little example here. We have our oscillator flapping away at 50 Hz, and let's say we've selected bank 1. So the inverse of that bank is 0, and for now let's say refresh is high. What's going to happen? We're going to have 0 on the output of purple gate 3, and we're going to have 1 on the output of purple gate 1. Okay, easy so far. What about further down the line? Well, the output of gate 4 is going to be oscillating with the oscillator. The output of gate 2 is actually just going to be 1 because it has a 0 going in. That's easy, it just gets inverted for 0 on the final bank select. I know I've got bank select 1 and final bank select 0, doesn't really matter. I suppose we could call them bank select A and B coming in on the left. The point is it's selected a bank, which is going to switch at some point. However, refresh is going to move much faster than 50 Hz. 50 Hz is glacial to refresh, so we should really represent that as a square wave, and that changes the output of gate 3 on the top there to a square wave. That changes the output of gate 2 to this. So let's think about it. While one of the inputs to gate 2 is low, that means when the oscillator input is low, we're always going to have 1 coming out. But while that input is high, when it's 1, it's going to oscillate with refresh. So we get this kind of square wave, masked way of passing refresh through. Half the time it's high and half the time it's oscillating with refresh. That means our final bank select is doing the same thing. Okay, it's inverted, but it's basically the same thing. So half the time it's 0, and half the time it's wobbling around with refresh. And what about if we selected bank 0 on the left hand side? Well, you guessed it, it all just flips upside down. We get the same thing, just the opposite. Okay, interesting. So why would we want to do this? Well, we need to look in a bit more detail. Let's just look at if we selected bank 0. We have this very technical oscilloscope diagram I've drawn of it oscillating between 0 and 1. Well, we need to look at where our bank select signal really goes. It goes into the input of this MUX chip, and I advise you to watch the previous video on the 80K mod if you haven't to see exactly what's going on here. And the signal is passed through the MUX chip under certain conditions when we're writing to or reading from memory. In fact, what happens is initially when we want to use memory, we pass through all of these 8 address bits. These are the outputs of the MUX chips, and they correspond to these inputs to the MUX chips I've highlighted brown. And this first batch includes our bank select signal, and then that is locked in with what's called a RAS signal into the upper memory chips. Then we switch through the remaining 8 address bits, coloured them in green here, and then that's locked in using the CAS signal. As I mentioned, this is what's happening when we're doing a memory read or write operation, but that's not the only time we address the upper memory. We also need to do that when we're doing a refresh operation, and when that happens, we're only outputting these 8 address bits, which is, if you like, the first 8 address bits which would normally get sent to upper memory. The need to refresh is a quirk of dynamic memory, and the upper memory in the spectrum is dynamic memory, or DRAM. Unless we refresh the DRAM, it will forget all of the data that it's meant to be remembering. The refresh operation is fairly simple. We just provide it with every possible address within this first half of the address bus, each time setting RAS, and every time we do that, we refresh that row of memory. Every single row of memory needs to be refreshed within 2 or 4 milliseconds, something like that, depending on the chip that we're using. Normally in a ZX Spectrum, we only need to use address bits A0 to A6 to refresh the upper memory. That's just how it's designed. It has a 7-bit refresh cycle. Every single row has to be refreshed within 2 milliseconds for the 4532 chips. The Z80 handles the refresh operation. Within the Z80 there's a 7-bit R register which stores a 7-bit address. Let's say we start from 0, it will refresh that row, increment to 1 and refresh that row. It's only doing this whenever it gets a spare moment at the end of each instruction cycle. And it keeps counting, and you get the idea, looping around when it reaches the end. And our bank select, which is normally held high, doesn't cause us a problem, but you might be seeing now why it might cause us a problem. With a mod like this, you would expect it to be sold with a full set of good upper RAM chips. Those could well be TMS4164 chips. If we look at the datasheet, we can see that this requires a 256 row refresh cycle, so A0 through A7 must be used, which presents a problem, right? It's good that it gives us 4 milliseconds to do it, that's twice as long for twice as many rows, handy, but we have a problem that we need to overcome. Because we're holding our bank select signal high, we're not going to refresh half of the memory. So let's revisit our final bank select signal, and it's starting to make sense now. While we're refreshing, it flips to the other bank, but this is at a time when there's a refresh happening. We're not actually making use of that bank, we're just using this to make sure that we pass through high and low on A7, half of the time high, half of the time low, or vice versa depending on which bank we've selected. So A7 during the refresh actually looks like this. So that's my theory. I think that this whole oscillator circuit and the final modification to the bank select is to enable us to refresh chips with a 256 row refresh cycle. Okay, good. Right, I'm going to put our circuit back together now because we want to start drawing the final thing, don't we? There's our little H joint which isn't used. I guess that's just our final bank select inverted, so let's call it that. I guess it's not being used on this machine, don't know why, or maybe it's actually for some kind of expansion, who knows. We need to finish the circuit now anyway and draw back in the first half of the circuit that we figured out so long ago. Okay, there it is. There's our flip-flops, there's our inputs, there's our A15 on-off mechanism. I'm just going to fill everything in now and connect up the bank select as well, and we have a beautiful mess. That looks crap, doesn't it? It's alright, I'm going to redraw it, so let's flip over to a more professional looking schematic. Here we go. Lovely. That's also hard to read, but at least it doesn't look quite so garbage. So let's remind ourselves before we actually have a go with the machine. When we start up, we'll get this initialization going on thanks to the reset signal, which should enable A15 and switch us to a particular bank of memory. Then we can use out0254 to disable A15, and I've picked 254 specifically because it's not going to switch the bank of upper memory that we're using. So what happens, we have our write command there. That's going to clock both of the flip-flops, which is great. The flip-flop on the left is going to set to D7, or the inverse of D7, and that will switch our output to low, and that's going to disable upper memory. There it goes, it gets flipped twice, and we get a 0 coming out constantly on A15. As for the bank, well, we've put in a even number, which is low on D0, which means the bank is going to stay at bank 1. This will crash the machine as expected, will reset, and the Spectrum will put the stack in lower memory. Alright, good. Then we do an out command, let's choose 126. That's going to switch upper RAM back on because we put a low in D7, and that flips the output of that flip-flop to high, which enables A15, and again we don't affect the selected upper memory bank. Now we can easily switch upper memory banks with a command such as out01. That's a odd number, that means D0 is high, means the inverted output of the flip-flop is going to be low, we're going to switch banks. Out00 will flip us back to the initial upper memory bank. Okay, easy. At any point during this, we can use the command print in and then address with A1 low. Let's just choose 1. This is going to give us a number, a decimal integer, and we can infer from that by checking out the values of D0 and D7 what the state of our two flip-flops is. All the while this is happening, we're going to have this oscillator flapping around at the bottom there, which will be modifying our final bank select half of the time based on refresh. So we get this profile coming out at the end, and those spikes correspond to when we have a refresh happening. Okay, is that it? I think we've explained everything now. Cool. So we're going to have a go with it, and I've made a little list of instructions that we're going to do to check out every possible function of this that we've figured out we think it should do. So let's get started. I've booted up the machine here. We're in our initialized state. So we can do print in 1, and we should get an even number which is less than 128. We get 126, that's right. Awesome. Let's disable upper RAM with out0254. And the machine resets, that's good. The stack is in the lower RAM now, I guess. And print in 1 is going to give us an even number above 128. We get 254. Awesome. Next bit, we're going to put upper RAM back on with out0126. And the machine doesn't reset now because the Z80 is happy using the stack in lower RAM. Print in 1 does return an even number under 128, so we're back to the initial state. Okay, we're going to try switching banks. First of all, let's poke in a value to upper memory. We'll poke into address 40,000, that's in upper memory, easy to remember. I'm going to use the value 42, obviously. Good. Now print peak 40,000 should give us 42, and yeah, it does, that's good. So let's try switching banks without 0, 1. This doesn't reset the machine, and our print in 1 command should return us with an odd number which is less than 128. We get 127, that's perfect. And we should be able to see what's in memory location 40,000, and it won't be 42, it's something else, some initialized value. So let's poke back in to 40,024, see if we can write to this other memory bank. And yes, we can, it's gone in. And when we print it back, we should see that 24 has gone in. Cool, so we can write to our other memory bank, nice. Let's switch back to where we started without 0, 0, and we should be able to read memory location 40,000, and we're going to get 42, which is what we initially wrote into there. Nice, so we're switching banks, that's great. And our print in 1 again returns an even number which is less than 128. Everything seems to be working fine. The last case is if A15 is disabled and we're in bank 0, we can get there by doing out 0255, and our print in 1 should give us a number which is odd and above 128. It gives us 255, so everything's working as we expected, which is fantastic. I did hook the logic analyzer up, and I can show you what's going on inside and show you that it matches what we expected. So here's a trace where I do a bank switch. Here's the selected bank at the top, so the bank switch is happening here where it jumps from 0 to 1. In the meantime, we have an oscillator, which is our 50 Hz oscillator, bouncing up and down, and as you can see, this is clocked, or seems to be synchronized to int, so whenever we get an int pulse low, it sets our oscillator value to 0, and then it flips back up to 1 halfway through the cycle, before going back to 0 in time with int. Awesome. So what else is interesting is our final bank output. As we mentioned, it's inverted, so where we have the selected bank 0, we get a 1 coming out. Again, it's just a bit confusing, I've called them 0 and 1 initially, we could call them A and B. And every other clock cycle of this oscillator, we can see that the refresh signal is being switched through. Now, unfortunately on this particular trace, it didn't seem to pick up refresh, but I have another trace here, which has a few more signals in. So we have refresh on the top, and as I mentioned, that's very rapidly oscillating around. And here's our final bank select on the second row. You can see half the time it's steady, low, if I zoom out, and half the time if I zoom all the way in, we can see that it is flopping around exactly in time with refresh as we expected. That's great. There is one big question here which I have. So half the time the final bank is low and half the time it's clocking with refresh, and we established that's probably to do with refreshing memory chips with a 256 row refresh cycle. But this is too slow. This is about 10 milliseconds, and really it should be 1 or 2 milliseconds in order to meet the requirements to refresh the chip. Now either I've made a mistake in reverse engineering this, or I've misinterpreted the function here, or the designers have made a bit of a cock-up and it should be faster. We could easily fix that by changing the value of the capacitor, but I'm not going to modify it, I'm just going to leave it like it is. So what do you think? Do you have an answer here? Have I got something wrong, or is it just a case of a little bit of ropey design work? Finally, I wanted to show you how this refresh pass-through is working, so let's just zoom out. Here's our bank select. Let's zoom in to a point where it's held low. We can see that every time refresh is low, we get a different address on the address bins here. These are 1, 2, 3, 4, 5, 6 of the address bits going into our memory. I don't have enough wires on my logic analyzer to give us all 8, but you get the idea. So whenever we're refreshing, we're putting through a different address on these bits, but every single time you can see that A7 is stuck low, matching our bank select. And you can see that as we cycle through all the possible rows in our memory, we're never going to get to that second half where A7 is 1, unless, let's move over to a point where we're switching through the refresh value onto our bank select. Now take a look. Every time refresh is low, the bank select goes high, which means A7 goes high, which is here. So every time we have a refresh in this state, we get A7 high, and we effectively refresh the entire upper memory, which is really nice. The only other question I have about this board is about interrupts. I did learn during the research around this that there is a type of interrupt IM2 which probably wouldn't work with a board like this. And when I saw that this was taking in the interrupt signal, I thought, hey, this has got some kind of mechanism to deal with that. But the only purpose that that seems to have is to synchronize the oscillator with the 50Hz interrupt from the Speccy. So I'm handing that one over to you as well. What do you think? Let me know in the comments or join on the Discord and let's have a chat about it in there. And I think that's about it from me. I think we've got to the bottom of it, or we've got as far as we can. We've got a schematic and we've proved that it works how we expected it to. Still not 100% convinced I've figured out everything that's going on here, so if you have spotted something, do comment below, and otherwise I'll see you in the next video. Thanks for sticking around till the end.